So let's proceed with the next talk, which is about deciding asynchronous hyperproperties for recursive programs, presented by Christoph Ohrem.
Okay. I think this should work. Okay, thank you for the nice introduction. As mentioned, the title of the paper is Deciding Asynchronous Hyperproperties for Recursive Programs, and this is joint work with Jens Gutsfeld and Markus Müller-Olm. Okay, so in recent years, a number of security flaws have been discovered, both in hardware as well as software systems. And in order to prove the absence of such security flaws in future systems, formal methods are required. A number of security properties characterizing the absence of such security flaws belong to the class of so-called hyperproperties. In a nutshell, a hyperproperty is a property of a system that depends on the relationship between different of its executions. So most of the work in recent years on the verification of hyperproperties has focused on so-called synchronous hyperproperties as well as finite state models. And while this may be adequate for hardware systems, it's not for software systems, especially ones featuring recursion. Here, a combination of asynchronous hyperproperties and pushdown models is a better fit. So in order, and while there's been some research on both of these features individually, there hasn't been any research on the combination of the two. And in order to address this gap in our research, we introduced a new asynchronous hyperlogic and also developed the first pushdown model checking algorithm for asynchronous hyperlogics. But before we go into the details of our contributions, let's first recall the notions of hyperproperties and asynchronous hyperproperties first. So classically in model checking, one has been interested in so-called trace properties. A trace is just an infinite sequence of sets of atomic propositions that hold along an execution of a system. You can see some examples here. And then a trace property is a property that may or may not hold on a trace. For example, a state satisfying P must eventually be reached. It's a trace property, and these can be specified, for example, using classical temporal logics like LTL, using the formula finally P. And then using this formalization, we can check for each of these traces individually whether they satisfy the specification, and in this example, each of them do. A hyperproperty, on the other hand, depends on the relationship between different traces. So an example would be the first occurrence of P is after the same number of steps on all traces. These properties require different temporal logics for their specification, like hyper-LTL. And you can see the specification of this hyperproperty on the slide. So the main differences to LTL and hyper-LTL are that the basic building blocks of formulas are propositions indexed by trace variables. So this P pi1 expresses that the proposition P holds on pi1, and using different trace variables then allows us to compare different traces with one another. And additionally, we have quantifiers binding these trace variables that range over a set of traces. And so hyperproperties on a more formal level are properties of sets of traces. Now, hyperproperties can also be characterized as synchronous or asynchronous. The intuition here is that is based on how we match different positions for comparisons when we evaluate a formula. In the example from the previous slide, this happens in a synchronous manner. So we count the steps on each trace. So we compare the first position with the first position, the second position with the second position, and so on. An example where this way of matching happens asynchronously is the number of occurrences of P is the same on all traces. One way to evaluate this hyperproperty would be to match the first P position on each trace with the first P position, the second P positions, and so on. And as you can see in this example, this way of matching is inherently asynchronous, and this makes this an asynchronous hyperproperty. So there has been some work on hyperlogics for the specification of asynchronous hyperproperties already. I picked out two examples here that are the main inspirations for our current work and that also highlight what is unsatisfactory about the current state of the art. So 3 years ago at POPL, my colleagues and I introduced the temporal fixed point calculus HMU. And while it captures asynchronous progress very nicely in general, its decidable fragments have some drawbacks like a high complexity or also issues with expressivity. Later, the logic stuttering hyper-LTL was introduced at LIX 2021. It captures only a subclass of HMU's hyperproperties, namely those where the asynchronicity can be described by stuttering. And while its decidable fragments have a nicer complexity, there are still issues with expressivity here. So to sum up, we have two main motivations for the current paper. First is that we think that the expressivity of decidable fragments of asynchronous hyperlogics can still be improved, and that is without affecting the complexity of finite state model checking. In order to address this, we introduce mumbling HMU in our paper, which is just a more expressive hyperlogic than stuttering hyper-LTL. Second, as mentioned on one of my earlier slides, all approaches to asynchronous hyperproperties that we are aware of use finite state models. So we consider pushdown models, which are able to model recursive programs much more precisely in our paper. So let me illustrate what is new about our logic mumbling HMU. So this slide is kind of full, but let's go through it together. So our logic is inspired by the logic stuttering hyper-LTL, but it has several additional features that are new. And I want to illustrate them with this example formula here. But before I go into the details of each feature, let me explain to you why this specification specifies this asynchronous hyperproperty. So the hyperproperty is, in observable positions, the traces of the system are indistinguishable with respect to a function f being in the call stack. So we have this formula here. It expresses that the function f is in the call stack on trace pi1. Then this part of the formula expresses that it is in the call stack on pi1 if and only if it is in the call stack on pi2. Then we have this next operator that advances each trace to the next observable position, and a fixed point that states that this happens repeatedly. Finally, we universally quantify over the trace variables to state that this happens for all pairs of traces of the system. So what are the features here that are in our logic but not in stuttering hyper-LTL? First, we have fixed points. These just generally give us expressivity compared to the usual LTL modalities that cannot, for example, express arbitrary omega regular properties. Then what's new is non-atomic tests. As you may have noticed, in hyper-LTL and also in stuttering hyper-LTL, the basic building blocks of formulas were atomic propositions tested on traces. Now here we have these brackets in which we can write trace formulas to test for trace properties on traces. So that's new as well. In these non-atomic tests, we can use Carré-like modalities. In a nutshell, these modalities allow us to inspect the call return behavior of traces generated by pushdown systems specifically. Then we have a simpler jump mechanism called mumbling, which I will go into more detail about on the next slide. And finally, we allow different jump criteria for different traces. In this example, this means that the observable positions on trace pi1 may be characterized in a different manner than the observable positions on trace pi2. So what is stuttering and mumbling, and why is mumbling more simple? So let me explain using these examples. Stuttering is defined using a set of trace formulas, and the stuttering next operator always advances to the next position where one of these formulas takes a different value. Mumbling, on the other hand, is much more direct. It's defined only using a single trace formula, and it always advances to the next position where this formula holds. Now, this is not only more direct and simple, it's also more expressive. In one of the more technical results of our paper, we were able to show that mumbling is more expressive when only LTL formulas are used in the definition of jump criteria. And while we were also able to show that the difference vanishes if fixed points can be used freely, this is due to the power of fixed points rather than due to the power of stuttering, as the first result suggests. So for the rest of the talk, I want to talk to you about our approach to pushdown model checking. Now, this is an inherently difficult problem for hyperlogics. As many of you may be familiar with, the emptiness of intersection problem for pushdown automata is an undecidable problem. And since pushdown systems are basically pushdown automata and hyperlogics allow us to compare different executions of systems, a reduction often leads to undecidability. Thus, restrictions are needed here. In our paper, we introduced the notion of well-alignedness. It's a restriction that we crafted to be as lax as possible so we can analyze as many systems as possible precisely. This example on the slide here should illustrate to you what is still allowed under well-alignedness. So you can see two finite subtraces with observable positions, and the height of these lines in between indicates the stack level. Now, at first glance, these traces look quite dissimilar. For example, the first trace goes onto a stack level that the second trace never goes to, and the second trace has some returning procedure calls that are unmatched by the first trace. Still, these traces are well aligned, and why is that? Now, there's some stack actions that cannot be pre-calculated by our algorithms. These are marked with arrows here, and since these stack actions are the same, namely two pushes, the traces are well aligned. Our approach to pushdown model checking then is to use well-alignedness in a well-aligned next operator, which in addition to its usual semantics expresses that the next step along the traces is well-aligned. This has an advantage over, for example, a global analysis where we only consider well-aligned sets of traces, because we can, for example, express that a set of traces is well-aligned, or we can restrict certain requirements to only pairs of traces that are well-aligned. And our approach to model checking is then to check for violations of this criterion in every step. Okay, so now that time is running out, let's come to my conclusion. Here's a summary of our contributions again, and our ideas for future work include, for example, an implementation of our pushdown model checking algorithm, a generalization of jump criteria beyond stuttering and mumbling, as well as using well-alignedness for decidable pushdown model checking in other hyperlogics. I thank you for your attention.
So any questions?
In your example, you had always two tracers for pi1, for pi2. It's limited, or?
No, there's also different ways to quantify. You can also use existential quantifiers. most of the interesting examples use multiple universal quantifiers. That's why I used them here. Maybe what's also noteworthy about this is that the complexity rises very quickly with the quantifier alternation. So in practical formulas, you only want to use maybe a single kind of quantifier.
Maybe just if I have only universal ones, but I have three properties, is there an interesting hyperproperty of that form? So pi1, pi2, pi3. You know any?
Actually, I'm not quite sure. I'm sure. So most of the examples where you have two universal quantifiers, they also already by transitivity go to the whole set. I'm not quite sure what a third universal quantifier would do there for you. The only example from the literature that has three quantifiers has different kinds of quantifiers, so I'm not sure there.
Other questions?
Just any kind of three quantifier property like transitivity or associativity, if you want to prove it for your program that computes a relation, that would be a hyperproperty with three quantifiers. If your system computes a relation and you want to say this relation is transitive, that would be a three hyperproperty with three universal quantifiers, I think.
Okay, I would have to think about this, but I guess this answers the question here.
Any other questions or answers? So maybe I can ask a question. You've presented well-alignedness. Is there any other restriction that you can combine with it to relax it?
Well, there's still some things you can do to relax it, but when you do, it becomes quite unnatural. So one of the things we require is that the stack level is the same on all positions, and you could theoretically still do an analysis when you have maybe a bound on how much the stacks are diverged on the observable positions. But if you do something like that, the restriction becomes quite unnatural, I think. And we used the most smooth, so to say, definition here that gives us that is not too restrictive, so to say.
Any other questions from the audience? Okay, I have a follow-up question on the implementation. Actually, have you experimented with benchmarks? How much does it scale? What's the kind of scale of the systems on which you have exercised it?
Actually, we haven't implemented our algorithm yet. That's why this point is in future work. Yeah. So we are aware for other hyperlogics that there are implementations, and it seems to scale a bit when you don't have quantifier alternations. And when you have your first quantifier alternation, you tend to have to use special techniques to handle those because the complexity becomes quite high. So already without quantifier alternations and finite state models, the problem is p-space complete, so the complexity is not that low.
I see. Okay. So I guess we can proceed with the next, if there's no other question. Okay, thank you very much.